Robots operating in challenging outdoor environments encounter a wide range of terrains from roads and cobblestones to dirt roads and grass. It is essential for them to be able to reliably classify such terrains for both safe and efficient navigation. This is an extremely challenging task as the visual appearance of outdoor terrain drastically changes over the course of days and seasons. Therefore, robots should be able to classify the terrains and adapt their navigation strategy, as solely relying on pre-existing maps is insufficient. Most state-of-the-art learning methods require a significant amount of data samples, which are often arduous to obtain in supervised learning settings where labels have to be manually assigned to data samples. Self-supervised learning, in contrast, allows the training data to be labeled automatically by exploiting the correlations between different input signals, thereby reducing the amount of manual labeling work by a large margin. The shown figure visualizes the overall information flow in our system. While acquiring the images and audio data, we tag each sample with the robot pose obtained using our SLAM system. We then project the camera images into a bird's-eye view perspective and project the path traversed by the robot into this viewpoint. We embed the audio clips into an embedding space using our proposed model. To this end, we leverage the visual properties of the patches of terrain traversed by the robot as seen from the onboard camera. The corresponding audio samples are obtained by selecting the audio clip that was recorded when the robot traversed the respective patch of ground. A triplet loss enforces that the embeddings of snippets with the same label are pulled together in embedding space and embeddings of samples with different labels are pushed away from each other simultaneously. We use an unsupervised heuristic to form triplets of audio embeddings by considering the visual features of the respective terrain patch images obtained with a pre-trained CNN. We observe that the closest neighbor in visual embedding space is likely to belong to the same ground truth class as the anchor sample. Therefore, we select the sample with the smallest distance in the visual embedding space as the positive sample, and we choose negative samples by selecting samples that are in a different cluster in visual embedding space than the anchor sample. Finally, we perform k-means clustering to separate the audio embeddings into clusters corresponding to the terrain classes present in the data set. We use these cluster indices to automatically label the corresponding robot path segments in the bird's eye view images. The resulting images serve as weakly labeled training data for the semantic segmentation network. Note that the entire approach is executed completely in an unsupervised manner. We gathered a large-scale data set with our robot Obelix equipped with a stereo camera mounted on top and a directional microphone mounted close to the wheels of the robot. We collected data on 5 different terrains, namely, asphalt, grass, cobblestone, parking lot, and gravel. We made our Freiburg terrains data set publicly available. We observed that for the majority of the scenes, the network trained with our approach is able to predict the semantic classes accurately. Our model is also able to segment more complex scenes with visual clutter. We observed that some misclassifications are produced due to high contrast shadows and visual ambiguities. The quantitative results demonstrate that our model provides better self-supervised generation of training data for semantic segmentation than the best performing unsupervised clustering baseline DEC. We note that our proposed model achieves comparable performance as the model trained in a supervised manner with manually annotated ground truth labels. We also employ our trained audio terrain classification model in previously unseen visual perceptual conditions to automatically label patches of terrain in images, in a completely self-supervised manner. The visual classification model can then be fine-tuned on the new training samples by leveraging transfer learning to adapt to the new appearance conditions. We demonstrate the utility of our framework for building semantic terrain maps. To build such a map, we use the poses of the robot and the terrain predictions of the camera images. We project each image into the corresponding location on a global map using the camera pose. For each image, we generate pixel-wise terrain classification predictions using our self-supervised semantic segmentation model. We then project these segmentation mask predictions into their corresponding locations in the global semantic terrain map, similar to the procedure that we employ for the bird's eye view images. For more details, check out our website and the paper at deepterrain.cs.uni-freiburg.de.